How are you, my kids, my students, and anybody who watch? Okay, today we're going to talk about right triangles. And right triangles are polygons with the three sides. Closed polygon is a closed figure with the straight lines. You know that. Okay, so we can today we're gonna construct two different right triangles. The first one I could use to draw just a line. For example, I can use start right here, my line. Okay. So if I would like my line to be 7 centimeters, I can start from this point and all the way to here. Okay, so I'm gonna make that line straight, and I will mark 2 points, 2.1 I call A, and I'm going to create, and I will make this right angle because its word says right angle. It has a right angle in it. So as you can see, this triangle has a right angle. So I'm going to use that tool to create a right angle. And I'm going to draw a line, little bit of line. So I'm going to think about, oh, I would like maybe 4 centimeters. So if or maybe 5. Let's do 5 centimeters. We get to, okay, so this is going to be 5 centimeters line. Okay, and here is my point B, and all I need to connect point C with point B, and I will have closed figure polygon called right triangle. Right triangle has a symbol that is like that. So why is the symbol used? Because if you take anything that has a right angle, if it will fit perfectly. And so this square sticker will fit perfectly in my corner of my right angle, and it will create a right angle. So that's why this little symbol is there to call right as a right triangle. When you see this little square, you know that is a 90 degrees angle. So after that, I can really prove that I have those 7 centimeters. So I can go in measure of mark each centimeter. So it's really 7 centimeters. So I can label this to be maybe A segment, and that is equals to 7 centimeters. And then I can mark these 5 centimeters here, and that I can call this as my B line segment, and that is 5 centimeters. CM stands for centimeters. And I'm going to measure how long is the in between. I want to mention something like even if my ruler has a less marked centimeters, like this one goes all the way to 8 centimeters, I can mark them like 1, 2, 3, 4, 5, 6, 7, 8 whole centimeters. But then I can extend anywhere in a point from the whole centimeter, and I can keep counting. I know there is 8 till here, and then I can see, oh, there is 1, 2, 3, 4, 5, 6. It looks like 7 millimeters. So my final measure for this BC line segment is 8, so I can call it C segment is equals 8.7 of the next centimeters, or 87 millimeters, or 8.7 centimeters. Then I can call this right triangle also scalene, because none of the sides, I can see 5 centimeters one side, 7 and 8.7, none of them are same. And then I can call that right triangle also a scalene triangle, because it's a part scalene as well. So we can write there nickname for scalene triangle. When we classified is by the sides, this will be scalene triangle, and by the angles, because it has a right angle, it's called right triangle. We also can label this triangle like triangle ABC, and then we can label sides. So we can say AB line segment is equals to 5 centimeters. Okay, well, we can see that BC line segment, a line above the letters explains line segment is equals to 8.7, 8 and 7/10 of a centimeter. And then CA or AC line segment is equals to 7 centimeters. Okay, we also can label angles. So angle A is 90 degrees. You know that. So the other two share other 90 degrees, because 90 plus 90 is 180. That's what we're looking for. All three angles in the triangles must add up to 180 degrees. So we needed to measure at least one of them in order to know what other one is. So if I choose to measure angle C, I can put my line on my protractor. That circle goes on a point. C center goes in a point. I make parallel to the edge, and then I make this and it look like that my angle is, if you look all the way from zero line all the way, it's in between 30 and 40, so that has to be 35 degrees. So point B, the angle C must be 35 degrees. Okay, we can label that angle by making arc and making arrows. The reason why we put arrows is because we can measure angle either way, from the BC to AC segment, or from AC to BC segment, because I can do this. I can put my line 0 to be on my my C, but other side. Okay, and then I can look, the 0 is inside, and I can say that here is the 0, 10, 20, 30, and 35 comes on my line in between 30 and 40 is 35, and that is my angle, 35 degrees. Okay, we know then this is 90 degrees. We don't label it, but we know it, so we can put 90 degrees plus 35 degrees. That will give us 125 degrees. And then we can think what other angle would be add up to that. So we will have 180 degrees, all three together. That's one way to think. Other way is if you know that these two are 120, then you can say 180 minus 120, and then you will 25, sorry, 125, and then you can subtract and you will get what the third angle is. So we can subtract 5 from 0, so we need to regroup. 10 minus 5 is 5, 7 minus 2 is 5, and our last angle, third angle, has to be 55. And we can prove it by adding here, like what 5 and what makes 0. So 5 plus 5 is 10, 0, I remember 1. And then you can see that what 1 and 2 makes 3, and 3 and what makes 8. So 3 and 5 is going to get you 8, and 100 plus 1. Nothing is 100. So we find out that is actually 55 degrees, and now we are sure 100%. And that is 55 degrees. I like to use a different color, so you know that this is the different color is a different size as well. So yellow is 90 degrees, orange is 35 degrees, and then pink I use for 55 degrees. So all three are different size. So then I can label, and goal B is 55 degrees. Okay. This is called scalene by the sides. None of the sides is the same, and also right angle because it has a right angle. If you know for the height, it would be the sides. If this is base, the height would be this AB side. So depend on what the height, what base you choose to be, to have that. If you choose base to be B and C, you can think the height to be this line right here. So that is important for sixth grade to know what would be height of this triangle. Now we're going to construct right triangle where it is going to have two sides the same. So let's have maybe 6 centimeters, one line. Okay, so if this is 6 centimeters, I want the other side to be also 6 centimeters, but it will be right angle. So I'm going to use my ruler. I can do any edge that it could work. It could be even my sticker could work for that. If I want to draw right angle, it would be useful to do so. Here is right. Okay, so now I'm gonna make sure that I measure 6 centimeters. So I'm gonna start from the back. Here is a 6, and I'll go all the way to 0. And this is 6 centimeters line. So sometimes you'll see that there is just a label like 6 centimeters. They don't label the segments are a lower letter and a 6 centimeters. If you like that way, it's okay. And then the last line segment will be in between these two. So I can put, this is A, B, C. Let's put this D, E, F. Okay, so those are points on each segment. So then we can say that this, we need this little square because that shows that is a right angle. Okay, right angle. And then we can label the sides D, E, line segment DE is congruent, and this is a symbol for congruent, equal sign, and then wavy sign on the top, is congruent to DE is congruent to DF. Line segment, and that is equals 6 centimeters. Okay. And then we can measure the other one. I also can measure this by adding or I could use my long ruler, and that would be about 8.7 centimeters also. 8.7, so 8. Let me see if it's correct. Could be 8.8. Say 8.6. I'll take 8.6 centimeters. 8.6 centimeters. About. Okay. So we can say that line segment EF is equals to about 8.6 centimeters. Depending how what precision I have. Okay, and so we know this is 90, and we know these two sides are equivalent or congruent. So these two angles have to be also congruent, because by the rule that if there are two equivalent congruent sides, there are two congruent angles that they share. So we know that 90 is this. So these two have to share 90. You can think that way. So as now 90 divided into 2 would be 45 and 45. So this has to be a 45 degrees. And then this also has to be 45 degrees. We can prove it by measuring with our I have another one. Okay, here we go. I can prove it by showing you this is the center for the circle. If you go from 0, you can go all the way to this line that is EF segment, and it stays right here in between 40 and 50, 45 degrees. So 45 degrees and 45 degrees. And all three will give you the 180 degrees, which is three angles in any triangle have to add up to 180 degrees, which is actually straight angle. If we cut these angles, pieces paper, we can put them together and they will create straight line, right angle. So we can say that angle D is equal to 90 degrees, and then angle E is congruent to angle F, and both are equal to 45 degrees. So another thing that some people um, make the lines for the for example, this one is they just slash it like this, and this are equal, so we know then if they are equal, these two are equal, and then this one is different, so that this one will have two lines. If it's that way, we can also so this, if I want to make this one is equal, so I will just put one line. This one will be two lines, and this one will be three lines, because none of them are the same. So we can measure and we can label that as well. We can explore the line of symmetry, and scalene right triangle does not have any line of symmetry. If I try to cut this way, this triangle and this part here is not equivalent. If I try to do any other way, it won't fit, and we can check it out. I created this. You see the triangle. Something similar. I did not have something that is slightly smaller, but that's okay. We can check because it's the same. And if you try to fold it, it will not be the perfect fit. So there is no line symmetry on this one. And if you imagine this cutting in this way, it will not give us the equivalent side. So anyway, and another thing is if we do and draw on a butcher paper, if we trace, that's another way how you can do this. If we trace this triangle, you can do it by hand if you want to, or use the ruler. We can see, does it has rotational symmetry? And we also can check line symmetry at the same time if we want. So if I put my dots right there, I can rotate the shape, and it will go all the way around, but it never gonna be back to the same exact form. So it goes all around until finally come back to where we started. And so we can say that this scalene right triangle does not have rotational. So it has zero zero line symmetry and zero rotational symmetry. And then we can explore the other one. I already draw a picture of this one, and if I put the dot in the top of E, I can rotate all the way around, and it's not matching. So the right triangle, scalene right triangle, does not have rotational symmetry either. But it has a line symmetry, because if I flip this paper, they will match perfectly. It will have line symmetry. So right there, you can see that this is the line of symmetry for a right triangle that is also isosceles. I created this little guy here, so I think it's gonna perfectly match. So this is the same right triangle, so the line of symmetry would be right here. Right there, because I will create two equivalent smaller triangles when I cut in the middle, and then they will perfectly fit. If I fold it in, there they will be. And that is actually the height of this right triangle. If this is called base. If this side DF is called base, then DE segment is the height of that right isosceles triangle. So we can write this as a nickname. This would be right triangle and isosceles triangle. So this triangle has one line symmetry and 0 rotational symmetry. Okay, what else to add? Students needs to know then if I add a congruent triangle on the top of the each of these, I will create a rectangle, and that's why the formula for finding area of each triangle would be the half of rectangle, because if I take my let's have my highlighter, and I take and create exactly the same triangle, right triangle opposite to one that I have, it will be created. I will be creating rectangle that goes around that triangle. And then my formula for area of one of the triangle would make sense, because if I look area for a triangle, I will just need to multiply the length times width to find the whole area of this rectangle, but I will cut in two in order to get just area of a triangle. And it's same thing right here. If I do that, I will have this. So if I have a right triangle, as you can see, and that has equal sides, if I add one more the same kind, I will have a square. And if I have the right triangle that is scalene, and I add one more, I will create rectangle. That's I can really explain with my little triangles. So I like my rulers. Just find another yellow one. There we go. So here is my one right triangle. It's like that one. And then if I add one more, I will create my square. I have a two right triangles, isosceles right triangle, and they will create a square. And then if I have, this is my one of my right triangle that is scalene, and then if I add another my triangular ruler that is same side, I will create rectangle. So if it's matching with this, like here, I can make that, and then I have another one here that will be making a rectangle. That's good. And that's why I found the area for whole, and then I take away one, and I will have an area of triangle. I hope that makes sense to you. We'll talk about that more. Thank you so much for watching. I appreciate your time, and have a great day. Love you.